Testing 1, 2, 3. Okay, should be recording. Let's go. We are doing lesson 4.3. Use linear models to make predictions. And so, lesson 4.1, we learned about scatter plots. And we graphed some scatter plots, that kind of stuff in lesson 1. So, lesson 2, we learned how to put a trend line on a scatter plot that models what the scatter plot does. Is it a positive association? Is it a negative association? Is it a weak association or a strong association? Okay, and then linear and nonlinear, right? So we looked at those things. Now today we're going to take those linear associations, we're going to put our trend line on there, and we're going to write the equation that goes with that trend line and use the equation to make predictions. Okay, so what two things do I need to write an equation? Y-intercept.
And the x, and the slope.
And the slope. We need those two things to write an equation. That hasn't changed. We needed those things for months to write the equations we've been working on, and now we still need those two things. But we're just going to have to look at our scatter plots. We're going to have to look at our trend line that we put on the scatter plot to find those two things. Okay? All right, so here we go. Today, our lesson essential. How do linear models help you make a prediction? So how do we use that equation to make a prediction? All right, warm up today. Not too bad. Bao, I guess, has a new tracking device that he wears when he exercises, sends data to his computer. How can Bao determine how long he should exercise each day if he wants to burn 5,000 calories per week? Okay?
That's unhealthy.
That's not unhealthy. 5,000 calories per week. That's good.
All right.
Yeah, that's fine.
So, can we put a trend line on our graph?
Yes.
Okay, would the trend line look like this?
Nope.
No silliness. Okay, it would not look like that. The trend line needs to follow the data. It needs to have about half the dots above and half the dots below the line. Okay, and so kind of freehanded one on there. That's not too bad. Would yours look maybe a little bit different than mine if you drew one? And that's okay, right? But they should be similar, right? And so when I look at, if think about, he wants to burn 5,000 calories per week. Okay, so how many calories would that be per day? How would I figure that out?
Divided by 7.
So 5,000
Divided by 7.
divided by 7, okay?
That'd be like 600.
It's gonna be a little over 700. 7 times 700 would be 4,900, right? So 5,000 divided by 7 is 714.28. 29, I guess. Okay, so we want to look at approximately 715 calories per day, right?
Yes.
715, about 715 calories. So where would that be on my graph? A little bit over 700. My line's about right there. So about how many minutes a day would he need to work out? About 80 minutes a day, okay?
That's a lot. Every day.
That's not even an hour and a half. Okay, so, okay, we're not judging, we're just looking. All right, so, does that mean that, what if he goes to the gym today and he only works out 60 minutes? That's all the time he has to do it.
And he just.
Well,
Then
Then maybe the next day he works 90 minutes, and the next day he works 90 minutes. He fits in those extra minutes when he can, and so he wants to average about 80 minutes a day for his workouts. If he can do that, then he's going to get close to that 5,000 calories per week. So one thing that's going to be a little bit different today, and we'll talk about this more as we go through. Some of the stuff that we'll talk about in this is like, usually with equations and writing equations, we want to know exact numbers, right? But with this, sometimes with trend lines and with making predictions and things, we're going to get close. We want to get as close as we can, but our numbers are going to vary a little bit. Your trend line is going to look a little different than mine. Your equation might even look a little different than mine, and that's going to be okay.
So we're just.
As long as they're close. Huh?
So like, basically
we're gonna sometimes have to approximate, and that's gonna be okay. Okay, all right, so, it makes it, does being able to approximate stuff, does it make it easier or does it make it harder?
Hard.
In some ways, it makes it easier because you just have to get close, but in other ways, it makes it harder because it's like, is my approximation good? Am I close enough, right? And so we'll see it go both ways a little bit. All right, let's move on. And, oh, look,
A video.
right? Here it is.
How does a linear model help you to make a prediction? Think about this question during the lesson. Michaela is a speed skater and hopes to compete in future Olympic Games. She researched the winning times for the past 50 years. If the trend in faster speeds continues at the same rate, how can she use the information to predict what might be the time to beat in 2026? What relationship might there be between the two measurements?
It's gonna be.
Okay, so what's happening with the speed of the time of the races that she's interested in?
It's going down.
It's trending downwards, so we're getting faster over time, right? So they're probably making improvements to the skates, they're learning new techniques, people are working out more, whatever. When you have a record, it just puts a number for somebody to beat, so somebody eventually is gonna get faster, right? And so that's what's happening. The trend is that the times are getting faster. And we gotta figure out if she wants to predict, like if I want to be an Olympian in 15 years from now, or 10 years from now, what speed do I need to be working for? Because if I'm just gonna match the speeds of today, people are getting faster. And I gotta be faster than they are. Okay.
There is a strong negative relationship between winning times and years after 1960.
Why is it a strong relationship?
Cause time's hard to
Because
beat.
all of the dots are close together.
Because the dots are close to the line, right? The dots aren't spread out all over the place. The dots are all really close to the line. So our trend line that means our trend line can be a really strong prediction. If the dots are all spread out, then our trend line might still be the right trend line, but it's gonna be a weaker projection. Like if we went back to that warm-up, the dots were spread out further away from the line than this one is. So our prediction is gonna be a little bit weaker. But this one, the dots are already close, so we should be able to make a strong prediction.
The trend line has a negative slope. The winning time tends to decrease from year to year. Our first step is to write an equation for the trend line. In order to write an equation for the trend line, we need to know the slope of the line and the y-intercept point.
What two things do we need to know to write an equation?
The slope and the y-intercept.
That's what we've been saying for months, and he just said the same thing. Okay, so here we go. Listen.
The y-intercept is about 2 4/10.
What did he just say there?
The y is about 2.4.
What weird word for a sentence or a math equation was in that sentence?
About.
About. How often do we say it's about that and we use that number?
No.
Not very often, but for this, that's what we're gonna have to do because that's the best we can do with the information we have from the graph, and it's okay. So it's about 2.4. That's gonna be good enough. It's gonna be close enough for what we wanna do, all right?
A calculator can help us find the slope. Rise over run is equal to negative 2/10 divided by 15.
He said you can use a calculator to calculate the rise over the run. That's because we know the formula to find the slope. What's the formula? Y2 minus Y1 over X2 minus X1. So, okay, so we know that formula and we can make that work. Using that formula and using a calculator to find the slope. A lot of times we wanted to leave our slope as a fraction, but in this case, decimals are gonna be okay because we wanna use those in the equation. All right, this is a weird activity. We're not gonna spend much time on it because they're taking us to this whole other thing. Look, in my algebra class, when we get to this lesson, and we do this stuff in algebra where we take it a lot further than we're gonna take it today, we actually do this. We go to a graphing calculator site, and we put stuff into a table, and the table, it plots it for us, and it shows us the perfect trend line. And then, you know what it does? It writes the stinking equation for us, okay, which is awesome. But we're also dealing with more complex stuff in the algebra class. So this lesson, they really do keep the numbers pretty okay for us to write our own equations. So for now, here's what's in your future. We're gonna make tables on a calculator, and the calculator's gonna do the work for us. For now, we're gonna learn how to do the work ourselves, okay? I don't even know why they put this in here, to be honest with you, because we're not doing this. All right.
Use the general formula y is equal to m times x plus b, where m is the slope and b is the y-intercept. The equation of the trend line is y is equal to negative 134 10,000ths times x plus 2 4/10. Now you can use the equation of the trend line to predict what might be the winning time in 2026. To make this prediction, we need to figure out what value of x to substitute into the equation. What value should we use?
Okay, so we wanna find out what,
Select your answer.
It's,
66,
why 66 and not 2026?
because it's not in 2026.
Well, that's the year that the Olympics are
Yeah, it's a
happening.
year.
But why is 66 correct? It is. 66 is
Is
correct.
it really? That's
No.
a guess, I don't know.
it's 26.
Because what does the x-axis say?
Oh, 1960.
Years after 1960.
Yeah.
Okay, so since 1960, the trend has been for 0.134 seconds, or that's minutes. So 0.0134 minutes per year gets taken off the best time. Okay, so we're talking about, you know, like just barely any seconds per year get taken off any time, less than a second per year. And then it's going down this much. So after 66 years, how much is it gonna be?
X represents the number of years between 1960 and 2026. So X is 66. Substitute 66 for X. Multiply, then add. If the trend in faster times continues at the same rate, Michaela should target about 1 51/100 minutes, or 1 minute 30 seconds.
Okay, so she wants to be a minute and 30 seconds faster than they were in 1960 to be, you know, to be able to get to an Olympic time in 2026. That's what the trend line tells us. Okay, so we're gonna do this. We're gonna look at a scatter plot. We're gonna put a trend line on it, or look at the trend line they have drawn for us usually, and we're gonna write the equation that goes with it. Okay, so here it is. Assuming the trend shown in the graph continues, use the equation of the trend line to predict average fuel consumption in miles per gallon. So this is our graph. This actually, these dots are all so close together. There is a trend line on there, but the dots are almost so close together it makes it hard to see the trend line. It would have been actually easier if they put fewer dots so we could see the line better, or made the line over the dots or something. But anyway, we need to pick two things. We need two things. We need our slope and we need our y-intercept, right?
Yep.
Can you see the y-intercept?
Yes.
Yep, it's about, it's 16.
Recalculate that in your mind. 15, because it's counted, the lines go by threes, 12, 15, 18, okay. So we know that the y-intercept is 15, okay? So then, now, the good thing about this is since I'm gonna find a y-intercept anyway, that can be one of my two ordered pairs to find my slope, right? Because I need two ordered pairs to find the slope. So one of my ordered pairs would be 0, 15. All right? Then I just need to choose another ordered pair that's on the line. And so as I look at this line, I can see that it goes through that point right there. Okay, so there's another ordered pair. What's that ordered pair?
20, 20, 20, 20.
2021.
Oh,
Okay, the horizontal lines go by 3, so 12, 15, 18, 21, 24. So it's 2021. So now I just need to find my slope. Y2 minus Y1 over X2 minus X1. So that's 21 minus 15 is 6. 20 minus 0 is 20. 6 over 20 simplifies to 3 over 10, which would be 0.3. Right? 3/10. Everybody with me?
Yep.
oh,
So 0.3.
wait, that's okay?
Having a decimal is okay.
I thought, well, you said before it was okay.
When we are concentrating on slope and we're counting the slope of the line, I want us to understand that it's rise over run, so I want to leave that as a fraction. But when we're going to use it in an equation, so that I can, multiply it by something, it's easier on your calculator to multiply by a decimal than it is by a fraction. If you leave it as a fraction, it's still right. There's nothing wrong with it. It's just going to be easier to use as a decimal. So in 2025, the average fuel consumption is predicted to be, well, what is the X value of our graph?
0.3 miles.
The X value of our graph
Oh.
is measuring what?
Years after
Years after
1980.
1980. And so we're talking about the year 2025. What number do I need to put in for my X then? How do I find it?
Oh, you,
How many years is it from 1980 to 2025?
it is
45 years. You would just subtract 2025 minus 1980. It's 45 years. Guys, some of this math is not super simple, but some of it is. Don't get tripped up on the simple stuff. You guys are not concentrating or something. So 2025, we would do y equals 0.3 times 45 plus 15. So 0.3 times 45 is 13 and a half. 13.5 plus 15 is going to be 28.5. So in 2025, the average fuel consumption is predicted to be 28.5 miles per gallon. All right. So that's it. I mean, writing the equation should feel familiar because we've done this for months. Literally for months we've been writing linear equations. Okay? So now we're having to write those linear equations based on a trend line that's on a graph with a bunch of other dots on it. Is this going to be a strong association or a weak association?
strong.
Very strong. The dots are all very close to the line. So it's a very strong prediction. All right. Moving right along.
Example 2.
So the scatter plot here shows the relationship between the number of people at a water park and the temperature. About how many people should the owners of the park expect at the water park when the temperature is 90 degrees? Guys, do we even need to write an equation for this?
No.
Because we can look at the graph. Sometimes writing the equation, if we're going to make a prediction about, something that happens out here, something that happens out here where I can't see what's on the graph, we might need to write an equation for it. But if we're going to make a prediction about something that's already on the graph, shoot, I can see that. It's right there. So about how many people should they expect when the temperature is 90 degrees? A little over 800.
Oh, yeah.
I mean, I think in your book, they even just, the answer to this one in the book says about 800, doesn't it?
I don't see. Oh, yeah.
Yeah.
800 people. at the water park.
I mean, they don't even round it up. I mean, it looks to me like the line's a little over 800. They don't even care. It's like about 800. It's close enough, right? Okay. So there's an example where, those estimating makes life easy on us. A bonus video!
Why?
I like this example too. This one's not too bad. Finding the y-intercept and the slope is pretty simple on this one.
The
Okay,
scatter plot
good practice
suggests
for us.
a linear relationship between two variables, the temperature and the number of smoothies purchased in thousands. Part A, What does the rate of change or slope represent in this situation?
What does the slope represent? Slope is what over what?
Oh, Y over X.
Rise over run, so what's the rise, tell me?
It's going up.
What, look at the graph. What does the rise mean on this graph?
Number of smoothies purchased.
Number of smoothies purchased per
10,000.
1,000, and what does the run tell me?
Temp.
The temperature. So as the temperature increases,
They purchase more smoothies.
more people buy smoothies. That's what the slope of the graph is telling me. You put it in terms of what the graph is labeled. So as the temperature increases, people buy more smoothies. Makes sense.
Yep.
The rate of change or slope describes the number of smoothies purchased for each 1 degree of temperature increase. How can you find the slope?
You know how to find a slope?
You
Y2
equals-
minus Y1 over X2 minus X1. We find two ordered pairs and we use the formula. That's what they're gonna do. I would choose, we need to find the Y-intercept anyway, right?
Yep.
I would always choose that one if you can see it, if you can use it. So that one would be 0, 8, and then I would choose another one where it's real easy to see. Maybe one like 80, 50, would that be 56? 80, 56? Would be an easy one to see. So I would use those two to find the slope. They're gonna use a little bit different ones, but pretty similar. Oh, shoot, I hit the wrong button, my bad. And then you gotta go to there. What does it mean? Were we on the next section here? Yep, okay.
To find the slope, begin by choosing 2 points on the graph of the trend line, such as the points with coordinates 40, 32, and 80, 56. The slope is equal to the difference in the y coordinates of the 2 points divided by the difference in the x coordinates. The fraction simplifies to 24/40, or 3/5. Part B. What does the y-intercept of the line represent in this situation?
For every 5 degrees. something
No,
else.
Y-intercept.
It represents the smoothie sold in temperature
At what temperature?
of 0 degrees.
At 0 degrees, how many smoothies do they sell?
Probably
No, look at the graph, 8,000. They sell 8,000
8,000.
smoothies on a day when the temperature is 0 degrees.
Ah,
I don't know what kind of thing they're running here, but wow,
Why would you buy a cold smoothie at 0 degrees?
maybe they're hot smoothies. I
The
don't know.
y-intercept of the line represents the number of smoothies sold when the temperature is 0 degrees Fahrenheit. The graph shows that the y-intercept is equal to 8. Part C. What equation relates the temperature, x, and the number of people who buy a smoothie, y?
We know the y-intercept, 8. We know the slope,
Yep.
3 over 5. So what equation would it be?
Y equals 3 over 5x plus 8.
Y equals 3 over 5x plus 8. All you gotta do is put those numbers into the equation.
Use the slope-intercept form of a linear equation, y equals mx plus b, in which m is the slope and b is the y-intercept. The equation for the line is y equals 3/5 x plus 8.
All right, that one wasn't too bad of an example because the numbers worked out really, really nicely for us. They left it as a fraction. It's an easy fraction to work with, so that one's not a bad one to leave as a fraction. If it comes out to a weird one like that first video where it was a weird decimal, then that's gonna be a weird fraction. So decimals are easier. All right, so a Smoothie Cafe has ingredients needed to make 50,000 smoothies on a day when the high temperature is expected to reach 90 degrees. Should the employees expect to have enough ingredients for the day's smoothies? Guys, we could use the equation. We could put 90 in for the X on the temperature. We could put 50 in for Y on the number of smoothies, or we got a graph with a line on it. Can you see 90 degrees on the graph?
Yes.
At 90 degrees on the graph, how many smoothies does it say they're probably gonna sell? a little bit less than 64,000. So if they got enough stuff to make 50,000, and it's gonna sell about 62,000, they're gonna have a bad day. All right, they're gonna run out of stuff, and people are gonna be mad, and they're not making all the money they should make. So they need to get some more bananas on hand real fast so they can make more smoothies, right? Okay, so there you go. All right, that's how we're doing this stuff. Use the graph when you can. It's easy. If you can't use a graph, if it asks for a specific number, you might need to use the equation to find that. All right. Your assignment, page 335, 336, 235, 236, right?
Yes.
Okay, I don't know why I keep saying 300s when I talk about numbers. 235, 236 is the assignment. Let's get to work.